let's move on to the next topic. This is called as the dynamics of circular motion. All right. So far we have seen that linear acceleration of a particle in the circular motion has fundamentally two components, right? First component is a tangential component, second component is called as a radial component, or it is also called as a centripetal force, right? And let us try to recall what equations we had written earlier. So the tangential net force is say, okay, let's write one sentence now. So this is what we already have studied. Okay, so that is, if in case of linear acceleration of a particle which is possessing the motion on a circular path, okay, so we can call it as in circular motion, has basically how many components? Two components. So what are the two components? They are tangential component and radial component. Tangential and radial. So normally whenever we have the forces along any direction, you can actually split that into two directions, right? In two different perpendicular axes, we can split the given force. So we resolve any force that is acting on the body also can be split into two directions, right? So similarly, so what we were talking so far was the acceleration. Acceleration, we try to split the acceleration into two directions, right? At the same time, since it is motion, we definitely have a net force that is acting on the body, because of which the body is under motion. So that means even the force can be split into the two directions, right? So similarly, we can resolve the force acting on the body, force on the body, or I can write the particle, in two different uh, directions. So once again, we will split into tangential and radial. So two directions, obviously, tangential and radial. So we'll not specify that. I'll directly go to what happens in the tangential direction. So in the tangential direction, what is the net force? We already have studied that, right? The net force is given by the mass of the particle, that's denoted by m, and the acceleration along the tangential, because F is equal to m into a, right? So that's how we write. So tangential direction force is, right, total force, net force is equal to this. At the same time, we can calculate the net force along the radial direction, right? So, and I'll also write the net force along the radial, along the radial direction, that is given by the mass into AR, that's the radius. So in case of a uniform circular motion, the tangential acceleration is zero. This is also we have studied. And hence, right, the net force in the tangential direction is also going to be zero, right? So this is because there is no acceleration in a uniform motion. So when acceleration is zero, we know that F equal to m into a. So that force also become equal to zero. Right, so let me write that point as well. This is these all these points we already have studied. This is just for us to recall what we had studied. Okay, so in case of a uniform circular motion, the tangential acceleration is equal to zero. So since the acceleration becomes equal to zero, the net force in the tangential direction, that also becomes equal to zero. Right, and in case of radial, let's calculate this, right? So therefore in the radial direction, what is the net force? F net is equal to, as per the fundamental equation, this is mass into acceleration in that direction. So you can see that this is m v square divided by, or you can also rewrite this as m into r into omega square. So all equations we are very well versed. So using the same thing, we also have written another form of the equation which can be used to solve problems. That is to find AR. Radial component of the acceleration is v square by r. So that's what we had used here. This is right. V square by r can be written as r into omega square. So this equation also we have used so far. Now we have a new name here coming up. So that is the net force which we have written now is always towards the center. So this F net is towards the center of the circular path, towards the center of the circular path, and it has a name and it is called as the centripetal force. So in most of the cases, the plane of the uniform circular motion will be horizontal and one of the tangent is in the vertical direction. So in such cases, we try to resolve the forces into horizontal radial, vertical tangential. Two components will be always present in case of a circular motion. All right, let's look at the applications to various cases. One very common problem that we see is related to, we'll look one after the other. So the first case is the conical pendulum. Okay, so in case of a conical pendulum, let's try to write a simple diagram explaining the concepts related to the conical pendulum. So there will be a point of a surface which is considered as a reference for us. So from this, I'll fix a point and from there I draw a line. Okay, let's assume that this is a string. On the top I have, at the end of this string we have a bob. It's a heavier object, circular in shape. Now, this is said to be a conical pendulum just because of the fact that it's not rotate, it's not actually having oscillations in a normal pendulum fashion. It's actually going to rotate on a circular path. So, okay, let's try to draw a circle. So this is the circular path. Let me assume that there is a radius r. So let me say this is an angle theta. So there is the object has a mass m, the bob has a mass m. So we know that any object which has certain mass will produce a force downwards because of its weight. So let's denote that as m into g. Okay, so there is a tension along the string denoted by capital T. Let's say the string length of the string is capital L. Okay, now, so what is the relationship between R and L? How do we define? Because we can see a triangle over there. So as soon as we see a triangle over there, I can also write one more notation here. If I try to extend, so if I try to extend, say this line like this, so there is an angle theta over here. This is also very useful. So same theta which is written over there, we can even find here. Okay, now, so the relationship between between the r and l using the theta, right? I can see that sine theta is equal to opposite, which is r, small letter r, radius divided by the length of the string l, capital L. So because of that, I can write the relationship like this. So small r is equal to capital L into sine theta. Call this as equation 1. So as we know now, the mass of the small bob tied to the string is m, right? And this oscillation, the circular pendulum oscillation, is called as a whirling. So it's whirled in the horizontal circle. So we can see that the path is circular, but since we are looking at an angle, this looks like an ellipse. All right. So in case of a conical pendulum, the vertical component of the tension balances the weight in the tangential direction. So that means the horizontal component provides the necessary centripetal force in the direction that is towards the center. So that means let's try to write the equation now. So the two forces which match are like this. One is its t sine theta. Okay, so t sine theta. So you see that that is the, if t is like this, t sine theta will be where? Will be the horizontal component, right? So if I write this, so I can change the color. So the t is like that. So what is the t sine theta? T sine theta is this one. The red colored arrow mark, what you see is the t sine theta. That's to the left. So that has to be compensated by the total net force in the radial direction, right? They have, it has to be opposite, right? So how do you make that happen? So this is equal to, make f net equation we just have written. So you can see that the net force is equal to, you can use either mv square by r, m r omega square, whatever. So I prefer writing in terms of the linear velocity, so I'll go ahead with, this is m into v square divided by r. So this is the centripetal force, this is the net force. They have to be equal, so they have to be cancelled. That's nothing but the first thing, that is the horizontal components of acting on the body of mass m, they have to be equal. Right, that's the first point. This is the fundamental equation we are going to use in case of a in case of a conical pendulum. Then another component is there. There is that's whatever is the weight of this object, that is mg, should be compensated by another force, that is the upward force, like this. So this force and this should match. So those are the two things which we need to write. We need to consider when we solve the problems, or when we write the equation, or when we try to model the problem related to the conical pendulum. Okay, so that means I'll write another equation. So the vertical component of capital T will be T cos theta, because theta is given with respect to y-axis. That is equal to the mass into the gravity. Okay, right? So these are the two equations which we write. Now, actually, we can go ahead and we can solve these equations. I'll call this as equation number 2. And we can actually find many other components as well. So how to solve that? Let me try to write. So this implies we can do a derivation here, but I'm going to skip that deriving part. I'll directly write the required answers. So using these equation 1 and equation 2, which we have written so far, just make one correction. Okay, this is m into g, mass into g for the acceleration due to gravity. Fine. So this, solving all the equations together, we will be able to find out the linear velocity v is equal to root of r radius g into the tan theta. Right, so we can divide one by other to get this. Another component which we can calculate is the angular velocity, omega. Omega is nothing but it is v divided by radius. So v is there already, right? I can simply try to write this is root of rg tan theta divided by r. So this r cancels as a root here. So that means I can try to write this is g times tan theta divided by r. That's the equation to calculate the omega. Then also we can calculate how much time the pendulum takes to cover or to complete one uh, oscillation, or how much time it takes to cover its complete path once. That is called as a time period. So also the time period of the pendulum. So we can calculate t is equal to, we have many equations possible, but I'll write the fundamental equation, that is 2 pi divided by omega. 2 pi by omega is what is going to get us this. So we can write multiple answers over here. One is 2 pi into root of r divided by g tan theta. All right. Also, you can rewrite this. You can make some modifications and you can write this as the answer. 2 pi into root of L cos theta divided by g. So either of these equations we can substitute, because here we substituted for r. R is equal to L sine theta. When we substitute that, we get the next part. So that's how we calculate this. Okay. This is the first case, which is called as the conical pendulum. Right. These are the equations required. Any question comes, we are going to use these equations. The next scenario is nothing but the motion of a particle inside a smooth cone. Let's try to write one. Okay, let's try to write one back. This is the center. Okay, now we'll create a cone starting from that, getting extended like this. At the same time, another one. So this is the cone, and the one what we are seeing now is the path, right, traversed by a particle which is present inside this cone. Okay, so now let me mark the particle over here. So it says this is a particle. That is a particle over here. That is actually taking that circular path. Now, what are the various forces that are felt? Right? From our basics, we know that one definite force which is acting downwards, perpendicularly downwards. So that is going to be the mass m into g. So assuming that the mass of the object is m, right? So this is always perpendicularly downwards. So I'll just write like this, indicating that this is coming downwards. Right. Another force which is going to act will be normal, right? Because the particle is touching a surface, so surface will push it back, right? So that is the normal component which we can draw like this. So this is a 90-degree to the surface. So I'll denote this as n. So remember, this is 90 degree. All right. Okay. In addition to this, let me say this is the center of the path. Okay, and okay, let's mark the radius now. So this is what we assume it to be radius. So denote this by radius r. And okay, one more very important aspect. So the conical shape is actually determined by one angle, right? That angle is with respect to the horizontal. So that is what we are going to mark like this. So if I consider this to be the horizontal surface, so this angle is the theta, which decides, right, how much slope you have. Smaller the degree, smaller the angle theta, right? So bigger circle, right? So cone will have a bigger circle. If you try to increase the theta, the radius of the circle reduces. Okay, now let's understand this. What exactly is going to happen? A particle is there whose mass is m. It is rotating inside the cone, which is considered as a smooth cone, right? So we try to use the word smooth here because we are assuming minimal forces acting on this body from the because of the surface. Okay. Uh, so what's the radius? Radius is r. Is a smooth cone. So the path along which the object is rotating is a circle held parallel to the original horizontal axis, or you can say that the horizontal circle, right? So the path traversed by the object is horizontal circle. What is the radius? It's r. Again, we assume that the speed is a constant. So I have to add that point now because I couldn't mark it over there. So we'll write let the speed of the particle be a constant value. So let's write it as b. Okay. Now, in such case, we can see only two forces acting on the particle, right? Again, we are also we try to mark the directions properly over here. One is the normal reaction, and one more is the weight, which is m into g. Now, we already have resolved the two forces in vertical and tangential direction and the horizontal radial direction. So what is the ultimate concept? Ultimate concept still remains same according to our previous case. The total vertical tangential direction net force should be equal to 0, right? That means vertical tangential direction and horizontal radial direction, right? I have to consider, and I have to make sure that the net force is equal to 0. So vertical tangential direction total force should be 0. So tangential vertical means this direction. Whatever force upwards should be matched with the downwards force. That's what is my first point that I need to apply. So that means what is the vertical force that is going upwards? Downwards is straightforward. It is m into g. What is the force upwards? Use this. If this is theta, if there is an angle theta over here, this will also be theta. That's the tilt which you get, right? So that means, right, I can write one equation now, very straightforward. This is n, vertical component will be cos theta. So this implies, these are the two equations. One is n cos theta should be equal to downward force, that is mg, equation 1. Similarly, if I try to write in this direction, what horizontal forces should match. Okay, so that means what is the horizontal component of n? That is n sine theta. So this should match, right? The net force acting on that particle which is rotating in circular motion, that is mv square by r. So equation number 2. So these two equations are required to solve. Okay, then we have another concept. So this concept is called as the death well or a rotor. So let us try to understand the scenario now. So it can be seen in various circus, or where people try to perform some stunts using bikes, bicycles, vehicles, or something. Right. Person drives a bicycle on a vertical surface of very large wooden wall. Okay. While uh, in case of a rotor, certain angular speed of the rotor or a person hands resting the wall without any support, okay, from the bottom. So that concept is what is called as a death valve, right? Normally they are at rest, right? But as soon as the performance begins, they start rotating. So this is the concept. Okay, so let me try to write a diagram representing what it is. This is a well made up of wooden, completely wood, let us assume. And so at a particular point, somebody is going to take this circular path, right? Somebody is going to ride a vehicle, ride their bicycle on this inner surface of this wall, right? Since it is, uh, since the walls are right angles to the horizontal, until and unless you reach a specific speed, you are not going to stay there. right? Because downwards force will attract. Okay, so now let's assume that this is the center and there is a radius of this circle denoted like this. This is the radius denoted by r. Now let me assume that the vehicle is at this point. I'll denote the vehicle by a circle, right? So this is the circle representing the whole mass of the object. Now we know that there are several forces that can act. The one force which is going definitely towards the center, we'll denote this because it is a surface, right? The surface is going to push the uh, object towards the center. So this is what is the normal. You see the normal becomes like this. Again, we have the forces like the object's weight downwards. So we'll write it as m into g, and the force to compensate that should be upwards. So let's denote this as the f. So basically we have only these variables present. Now in such case, the frictional force is going to balance the weight of the person and the vehicle, and the reaction at the wall is going to provide the required centripetal force for this motion. So it's something like okay, let's try to write like this. So what is the concept, how the person is able to do this stunt by moving the vehicle on this path? That is because there is a F which is the frictional force. That frictional force is going to balance the weight of the bike plus person. So I'll write the frictional force, write F, balances the weight mg. Okay, so that means the F friction should be equal to m into g in this case. That's the first equation. And the second equation that comes because we need a centripetal force. We need to keep attracting the object towards the center of the circle. If a object has to move around that circular path, right? So that's the requirement. So obviously it means that the reaction provides the centripetal force of the circular motion. So right, the reaction N provides the centripetal force of circular motion. So denote that N should be equal to what's the net force? That is m into v square by the radius, or you can also write it as m into r into omega square. All right. Now let's move on to the next case where we apply these concepts. So this is whenever we are running on a track which is circular. Maybe that's the first case. Otherwise, uh, a bicycle or a cyclist is moving around a circular path, or there is a turning, right? And he wants to pass the turning at a high speed. So you will observe that in all such cases, we try to bend towards the center on a circular path. So I'll try to write the side heading like this. Maybe it's a cyclist bends towards the center whenever on a circular path. Okay, right. Now, okay, let's try to denote something. So let us say this is a horizontal plane, and uh, the cycle touches the horizontal or the ground at a point, which means there is always a normal reaction in this direction, that is n. I assume that this is the point where the tires of the the bicycle touches ground, right? So I also know that because of this, okay, let me assume something. So let me assume that the bicycle is, this is the plane of bicycle. Okay, so bicycle is actually situated over here. Let's assume. Now, with respect to vertical, the bend is by an amount equal to measured in angle. So this angle, let's assume that this is theta. Okay. At the center of the bicycle, the whole weight is concentrated, right? So at that point, we can assume that there is a weight of the bicycle plus whoever is the rider. All right. So that actually falls down here. That is equal to m into g. So there will be a frictional force horizontal like this denoted by F. So this is the G, the point where whole mass is assumed to be concentrated for the given bicycle plus the right. So since that is theta, this is also going to be the theta. Okay. Now, from this particular figure, we will be able to write one equation straightforward, that is equal to if we try to calculate the net force. What is the net force? I know that the net force on this will be something like this. This is what I denote as capital F. Right? From this figure, this implies I can write capital F is equal to, under the square root, this is n square plus the F square. Right? Because F is, right, the resultant of capital N and small f. So when the cyclist is inclined to the center of a circular path, the resultant of capital N, which is the normal reaction, and F, which is the horizontal or it's a friction, as well as the result of that mg, which is acting downwards, right, is always directed horizontally to the center of the circular path. All right. So why it is to the center of the circular path, I'll show you another day. So this actually can be equally rewritten like this. Now, let us assume that this is the point of contact. I'll try to draw this in a slightly different pattern. Let's me assume that a different shape. This is the overall structure. So at the center, I have, this is the center G, which we were considering so far. Okay, now you can see that N and F resulted in capital F. So whatever N, that is a normal reaction, and the small friction F, the resultant of that is nothing but the capital F. Okay, I hope that is clear, right? So the F is like that. Now you see, F is here, mg is here. I have to find the resultant of that. Okay, I need to find the resultant. Let me try to write the resultant of F and this. So let me mark the F first. Okay, so this is the F. And at the same point, let me assume this is the mg. Right? Now, how do you calculate the Okay, I just have to reduce this a bit. Okay. So to calculate this, we draw the parallelogram. Okay, let me draw the parallelogram here. I'll extend the other force. So just to match this. Okay, why we are doing this? Because this has to match. This has to come to the center. So what we do, we'll finish the parallelogram. So this is the parallelogram. And now we know that the diagonal of the parallelogram is going to give you the resultant. Now you see the resultant is, this is the F, right? This is the F. This is mg. Resultant is horizontal. That's why the body is going to bend to the right, right? So the net force is this. That is the direction of the total force denoted by m, denoted by m v square divided by r. So we can try to write the equations in different format. The total equations, the overall equation which governs everything, I'll try to write all the equations. So tan theta, if you want to calculate, you can use this equation, that is F frictional force divided by the normal reaction, right? So in this case, we can try to write F, which is a frictional force, where F is equal to, friction should match our net force, that is m v square divided by r. And what is n? N can be calculated as mass into this. So overall, I can write this implies my general equation will be tan theta is equal to, after substitution of mv square by r and mg over there, you get v square divided by r into g after simplification. Okay, so these are the equations that one can use whenever we try to solve the cyclist bending towards the center.